JWST discovered red dots that appeared in images of the early universe. They showed up when the universe was less than 1 billion years old. Then, around 2 billion years after the Big Bang, they vanished. For 3 years, astronomers had no explanation. Too bright to be star-forming galaxies, too quiet to be black holes. Published January 15, 2026 on the cover of Nature, 3 teams now think they solved it. And all 3 answers are different. Right now, the leading hypothesis is that little red dots are young supermassive black holes shrouded in dense cocoons of ionized gas. The cocoons scatter electrons, broadening spectral lines and making the black holes appear 100 times more massive than they actually are. When corrected, the black holes weigh 100,000 to 10 million solar masses, not billions. The cocoons also block X-rays and radio waves, explaining why little red dots are almost invisible in those wavelengths despite being powered by black hole accretion. The data comes from the highest quality JWST spectra ever obtained. Vadim Rusakov from the University of Manchester led the study. His team analyzed 12 little red dots and found that spectral lines are broadened by electron scattering through a Compton-thick medium, not by bulk Doppler motions from gas orbiting massive black holes. The intrinsic line widths are only 300 kilometers per second, not 2,000. That reduces the inferred black hole masses by 2 orders of magnitude. Dr. Darach Watson from the University of Copenhagen, co-author of the Nature study, stated, "The little red dots are young black holes, 100 times less massive than previously believed, enshrouded in a cocoon of gas, which they are consuming in order to grow larger. This process generates enormous heat, which shines through the cocoon. This radiation through the cocoon is what gives little red dots their unique red color." Still more striking, a competing hypothesis from Harvard's Center for Astrophysics suggests little red dots are not black holes at all, but supermassive stars. These stars, roughly 1 million times the mass of the Sun, would produce the exact same spectral signatures. A third hypothesis, published in February 2026, proposes that self-interacting dark matter halos collapsed into seed black holes in the early universe, providing the initial mass that grew into the black holes we see in little red dots. Here is what should concern you most. If little red dots are young black holes caught in a brief phase of rapid growth, then we are seeing supermassive black hole formation in real time. But if they are supermassive stars on the verge of collapsing into black holes, then we are witnessing the birth mechanism itself. And if dark matter seeded them, then black holes and dark matter are connected in ways we never predicted. Think about that. Before we break down 3 years of scientific debate and 3 competing solutions, if you want to stay updated on discoveries that rewrite our understanding of the early universe and black hole formation, hit subscribe and turn on notifications. Because what we are about to reveal will change how you think about the first billion years after the Big Bang. Leave a comment telling us, which hypothesis do you think is correct? Electron-scattering cocoons, supermassive stars, or dark matter seeds? Let's start with the discovery. In December 2021, JWST captured its first images. The telescope's infrared sensitivity allowed it to observe galaxies formed in the first few 100 million years after the Big Bang. Among those galaxies were compact red objects that appeared in multiple deep field surveys. They were dubbed little red dots because of their appearance in JWST images, small, red, and unlike anything seen before. Little red dots have several defining characteristics. First, they are spatially compact. They appear point-like or nearly point-like in JWST images, with sizes less than 1 kiloparsec, often much smaller. For comparison, the Milky Way is approximately 30 kiloparsecs in diameter. Little red dots are hundreds of times smaller. Second, they have distinctive V-shaped optical UV spectra. The spectrum shows a sharp change in slope near the Balmer limit at approximately 365 nanometers. Below that wavelength, the spectrum drops steeply. Above it, the spectrum is relatively flat. That V-shape is characteristic of little red dots and distinguishes them from typical star-forming galaxies or active galactic nuclei. Third, they exhibit broad hydrogen and helium emission lines. The hydrogen alpha line, in particular, shows widths of thousands of kilometers per second when measured in the traditional way. Broad lines indicate rapid motion, typically interpreted as gas orbiting close to a supermassive black hole. But little red dots have a problem. The inferred black hole masses are too large for their host galaxies. Fourth, they are extremely X-ray and radio quiet. Supermassive black holes actively accreting gas should emit strong X-rays and radio waves. Little red dots emit almost none. Multiple studies with Chandra X-ray Observatory and radio telescopes found little red dots to be orders of magnitude fainter in X-rays and radio than expected for their inferred black hole masses and luminosities. But the mysteries don't stop there. The mystery deepened when astronomers realized little red dots exist only in a narrow redshift range. They first appear at redshifts around Z Prarner 4 to 5, corresponding to roughly 1.2 to 1.5 billion years after the Big Bang. They are most common around Z Prarner 5 to 7, approximately 700 million to 1 billion years after the Big Bang. And they seem to disappear by Z Prarner 2 to 3, around 2 to 3 billion years after the Big Bang. That temporal window is significant. It suggests little red dots are not a permanent class of objects, but a transient phase in the evolution of galaxies or black holes. Something about the early universe, or the early stages of galaxy and black hole formation, allowed little red dots to exist. And something changed after 2 billion years that caused them to vanish or evolve into something else. Initial interpretations fell into two camps. One camp argued that little red dots are heavily obscured active galactic nuclei powered by supermassive black holes. The broad lines indicate black hole masses, and the compact sizes indicate dense nuclear regions. The X-ray and radio weakness could be explained by extreme obscuration from gas and dust surrounding the black hole. The other camp argued that little red dots are young galaxies undergoing intense star formation. The compact sizes and high luminosities could result from starbursts concentrated in small regions. The broad lines could be produced by supernovae-driven winds or other stellar feedback processes, not black hole accretion. Both interpretations had problems. If little red dots are obscured black holes, the obscuring material would need to be extraordinarily dense to suppress X-rays and radio waves to the observed levels. Typical dusty tori around active galactic nuclei cannot achieve that level of suppression. If little red dots are starbursts, the star formation rates would need to be implausibly high, and the broad lines would require wind velocities inconsistent with stellar feedback models. Here's where it gets really strange. In 2024 and early 2025, several studies attempted to resolve the debate. Some used JWST's NIR spec instrument to obtain high-resolution spectra of little red dots, measuring the shapes of emission lines in unprecedented detail. Others used ALMA to search for molecular gas and dust, testing whether little red dots have the cold reservoirs needed to sustain star formation. Still others used X-ray and radio follow-up observations to constrain the properties of any hidden black holes. None of those studies provided a definitive answer. The data were consistent with both black holes and star formation, depending on the assumptions made in the analysis. The debate remained unresolved as 2025 ended. Then, in January 2026, 3 papers were published within days of each other. Each claimed to have solved the mystery, and each proposed a different solution. The first paper, published January 15, 2026, on the cover of Nature, was led by Vadim Rusakov from the University of Manchester and Darach Watson from the University of Copenhagen's Cosmic Dawn Center. The team analyzed the highest quality JWST spectra of 12 little red dots, focusing on the shapes of the broad emission lines. Traditional analysis assumes that broad lines are broadened by Doppler shifts from gas orbiting the black hole. The velocity width of the line is related to the mass of the black hole through the virial theorem. If the line width is 2,000 kilometers per second and the gas is orbiting at a certain radius, the black hole mass can be calculated. Rusakov and Watson's breakthrough was recognizing that the line shapes are not Gaussian, as expected for Doppler broadening. Instead, they are exponential. When plotted on a semi-logarithmic scale, the lines trace straight lines over several orders of magnitude. That is the signature of electron scattering, not Doppler broadening. Electron scattering occurs when photons emitted near the black hole collide with free electrons in surrounding ionized gas. Each collision changes the photon's direction and slightly shifts its wavelength. After many collisions, the photon's wavelength is randomly shifted, creating a broadened line. The shape of the broadening is exponential if the electron column density is high. The electron column densities required are enormous. Rusakov and Watson's models indicate electron column densities of approximately 10^24 to 10^25 electrons per square centimeter. For comparison, the electron column density through Earth's entire atmosphere is about 10^22 electrons per square centimeter. The cocoons around little red dots black holes are 100 to 1,000 times denser. At those densities, the gas is Compton-thick. Compton-thick means that X-ray photons cannot penetrate the medium without being scattered or absorbed multiple times. X-rays produced by the accretion disk around the black hole are absorbed by the dense gas before they can escape. That explains why little red dots are so X-ray faint despite being powered by actively accreting black holes. The compactness is also critical. The cocoons must be only light days across. A light day is the distance light travels in one day, approximately 26 billion kilometers, or about 175 times the distance from Earth to the Sun. That is extraordinarily small on astronomical scales. The compact size, combined with the high electron density, creates the extreme optical depths needed to produce the observed exponential line profiles. And the data showed something that simulations hinted at, but observations had not confirmed. Rusakov and Watson modeled the lines as a combination of a narrow intrinsic Gaussian core and an exponential electron-scattering component. The narrow core represents the true velocity of gas near the black hole. The exponential wings represent scattering by the cocoon. Fitting that model to the data, they found that the intrinsic line widths are only 300 kilometers per second in most little red dots, not 2,000. That changes everything. If the intrinsic velocity is 300 kilometers per second instead of 2,000, the inferred black hole masses drop by a factor of 40 to 100, depending on the object. Black holes previously thought to weigh 1 to 10 billion solar masses actually weigh 100,000 to 10 million solar masses. They are still supermassive, but they are young supermassive black holes, not fully grown ones. Dr. Rusakov stated, "This cocoon makes these black holes look red and prevents much of their radiation from escaping and explains why they look so compact. Without the ionized gas, the data simply don't make sense." The cocoon model also explains the missing X-rays and radio waves. X-rays are absorbed by the dense ionized gas through photoelectric absorption. Radio waves are suppressed because the gas is so dense that synchrotron emission cannot escape. The cocoon acts as a shield, blocking most of the electromagnetic radiation except for optical and infrared light that scatters through it. The cocoon masses are estimated to be tens of solar masses. The black holes are accreting close to the Eddington limit, the maximum rate at which a black hole can accrete without blowing itself apart through radiation pressure. The cocoons are not spherical. Radiative transfer models indicate that the gas must have both inflowing and outflowing components, with comparable amounts of each. The inflowing gas feeds the black hole. The outflowing gas is driven by radiation pressure. Dr. Rodrigo Neman from the University of São Paulo, who wrote an accompanying commentary in Nature, noted, LRDs once seemed to demand either impossibly efficient galaxy formation or implausibly massive black holes appearing out of nowhere in the young universe. Either way, something was badly wrong with our models. But with their estimated masses downsized per the Nature study, any black holes within LRDs would be easier for pre-existing models to account for. Not all astronomers immediately accepted the cocoon model. In September 2025, a team from the University of Cambridge published a challenge to the electron-scattering hypothesis. They analyzed the Rosetta Stone little red dot, one of the brightest known LRDs at redshift Z-226. Using multiple hydrogen recombination lines, H-alpha, H-beta, and Paskin beta, they showed that the lines have different spectral profiles, which is inconsistent with simple electron scattering. If electron scattering dominated, all hydrogen lines should show the same exponential shape because the scattering depends only on the electron density and optical depth, not on the specific transition. The Cambridge team found that the lines do not match, suggesting that electron scattering is not universally applicable to all little red dots. Vadim Rusakov acknowledged the challenge in subsequent comments, noting that the detailed physics inside the gas cocoon is still an open area of research. The implication is that some little red dots may be powered by electron scattering cocoons, while others may have different mechanisms. The population of little red dots may not be homogeneous. Some may be black holes with cocoons. Others may be supermassive stars. Still others may be transition objects where stars are collapsing into black holes. But there's another problem that nobody expected. Just days before the Nature paper was published, another team released a competing hypothesis. On January 6, 2026, researchers from Harvard's Center for Astrophysics, led by Devesh Nandal, announced that little red dots might not be black holes at all. Instead, they could be supermassive stars. Supermassive stars are hypothetical objects with masses around 1 million solar masses. They are not the same as supermassive black holes. They are stars, fusion-powered objects with cores generating energy through nuclear reactions. but they are so massive and so extended that they look and behave very differently from normal stars. Nandal's team created detailed physical models of supermassive stars with masses around 1 million solar masses, assuming metal-free or low metallicity compositions appropriate for the early universe. They calculated the star's spectra, including the shapes of emission lines, the continuum shape, and the overall luminosity. The results matched little red dots perfectly. The supermassive star model produces a V-shaped spectrum with a break near the Balmer limit. It produces broad hydrogen emission lines with widths consistent with observations. It produces high luminosities concentrated in small regions, consistent with little red dots' compact sizes. And it naturally produces the red color because the star's outer layers are cool despite the hot core. Nandal stated, "Little red dots have been a point of contention since their discovery, but now, with new modeling, we know what's lurking in the center of these massive objects, and it's a single gigantic star in a wispy envelope. The supermassive star model does not require electron scattering, dense cocoons, or black holes. It explains all the observations with a single massive star. If correct, little red dots are not black holes growing rapidly in the early universe. They are short-lived precursors to black holes, giant stars that will collapse into black holes within a few million years." The supermassive star hypothesis is attractive because it explains why little red dots disappear after 2 billion years. Supermassive stars are unstable. They cannot exist indefinitely. They will collapse either directly into black holes or through intermediate stages involving pulsations or mass ejections. If little red dots are supermassive stars, they vanish when the stars collapse. Why are supermassive stars unstable? The problem is radiation pressure. A star generates energy in its core through nuclear fusion. That energy flows outward, creating radiation pressure that pushes against the star's gravity. For a star to remain in equilibrium, radiation pressure and gravity must balance. For very massive stars, radiation pressure becomes so strong that it exceeds gravity. The star begins to lose mass through winds or eruptions. If the star is massive enough, radiation pressure can drive pulsational instabilities where the star expands and contracts repeatedly. Eventually, the star collapses. For supermassive stars with masses around 1 million solar masses, the timescale for collapse is only a few million years. That timescale matches the observed duration of little red dots. If little red dots appear at z-5 to 7 and disappear by z-2 to 3, they exist for approximately 1 to 2 billion years in cosmic time. But due to time dilation, the proper time experienced by the objects themselves is shorter. A supermassive star that collapses within a few million years of proper time would appear to exist for hundreds of millions to billions of years in cosmic time when observed at high redshift. Nandal's team emphasized that supermassive stars avoid the need for exotic physics like electron-scattering cocoons or dark matter halo collapse. Supermassive stars are predicted by stellar evolution theory. They form naturally in metal-poor environments with high gas densities, conditions that existed in the early universe. If little red dots are supermassive stars, no new physics is required. But there's a third hypothesis. On February 3, 2026, Fangzhou Jiang from Peking University and collaborators published a paper in the astrophysical journal Letters proposing that little red dots, black holes, formed from the collapse of self-interacting dark matter halos. Self-interacting dark matter is a variant of the standard cold dark matter model, where dark matter particles can collide with each other and exchange energy. In regions where dark matter is very dense, those collisions can cause the dark matter to collapse into compact objects. Jiang's team performed semi-analytic modeling to explore whether self-interacting dark matter halos could collapse into black holes in the early universe, and whether those black holes could grow to the masses observed in little red dots. They found that the answer is yes. Dark matter halos with masses between 10^6.5 and 10^8.5. Solar masses could collapse into seed black holes with masses between 10^4.5 and 10^6.5 for solar masses by redshift z-8.5 when the universe was less than 600 million years old. Those seed black holes would then grow through accretion and mergers. By the time little red dots are observed, around z-5 to 7, the black holes would have masses of 10^5 to 10^7 solar masses, consistent with Rusakov and Watson's downwardly revised mass estimates. The dark matter halo collapse provides the initial mass needed to jumpstart black hole growth, avoiding the problem of how supermassive black holes formed so quickly in the early universe. Jiang and collaborators noted that their model is sensitive to the dark matter self-interaction cross-section and other parameters, but the general result holds. Self-interacting dark matter can produce seed black holes at high redshift, and those seed black holes can grow into the objects observed as little red dots. Now let's put everything together. 3 hypotheses. Hypothesis 1. Electron-scattering cocoons. Little red dots are young supermassive black holes with masses of 10 Merber 5 to 10 Merber 7 solar masses, not 10 Merber 9 to 10 Merber 10. They are enshrouded in dense cocoons of ionized gas with electron column densities so high that photons scatter many times before escaping. The scattering broadens spectral lines, making the black holes appear 100 times more massive than they actually are. The cocoons block X-rays and radio waves. The cocoons have tens of solar masses of gas, both inflowing and outflowing. The black holes accrete near the Eddington limit. This is the leading hypothesis, published on the cover of Nature, January 15, 2026. Hypothesis 2. Supermassive stars. Little red dots are not black holes, but single supermassive stars with masses around 10 more 6 solar masses. The stars are metal-free or low metallicity, appropriate for the early universe. They produce V-shaped spectra, broad emission lines, compact sizes, and high luminosities naturally, without requiring black holes. The stars are short-lived and will collapse into black holes within a few million years, explaining why little red dots disappear after 2 billion years. This hypothesis was published by Harvard CfA, January 6, 2026. Hypothesis 3. Dark matter seeds. Little red dots black holes formed from the collapse of self-interacting dark matter halos in the early universe. The halos collapsed into seed black holes with masses of 10^4.5 to 10^6.5 solar masses by Z^8.5. Those seeds grew through accretion and mergers into the 10^5 to 10^7 solar mass black holes observed in little red dots. This hypothesis connects black hole formation to dark matter physics and explains how supermassive black holes formed so quickly. Published in ApJ Letters, February 3, 2026. All 3 hypotheses explain the observations. Electron-scattering explains the broad lines, the cocoon explains the missing X-rays and radio, and the downsized masses solve the overmassive black hole problem. Supermassive stars explain the spectra, the compact sizes, and the transient nature of little red dots. Dark matter seeds explain the initial mass and the rapid growth timescales. We are not saying one hypothesis is definitively correct. The Nature paper has the most detailed spectroscopic data and the most comprehensive modeling, but the supermassive star model cannot be ruled out based on current observations. And the dark matter seed model is consistent with both the electron-scattering cocoon interpretation and the supermassive star interpretation. Dr. Watson stated, "We have captured the young black holes in the middle of their growth spurt at a stage that we have not observed before. The dense cocoon of gas around them provides the fuel they need to grow very quickly." And here is what this really means. We are witnessing supermassive black hole formation in the early universe. Whether the mechanism is accretion onto seed black holes formed from dark matter collapse, or the collapse of supermassive stars into black holes, or rapid growth of smaller seed black holes within gas cocoons, the end result is the same. Little red dots show us how the universe built its first supermassive black holes less than 1 billion years after the Big Bang. So what do we know for certain? Little red dots exist. They appeared when the universe was less than 1 billion years old and vanished around 2 billion years after the Big Bang. They are compact, red, and exhibit broad hydrogen emission lines. They are extremely faint in X-rays and radio waves. JWST has detected hundreds of little red dots across multiple deep field surveys. What don't we know? Whether little red dots are black holes, supermassive stars, or a mix of both. Whether electron scattering is the dominant line-broadening mechanism, or whether other processes contribute. Whether dark matter played a role in seeding the black holes. And whether the transient nature of little red dots is due to stellar collapse, cocoon dissipation, or changes in accretion rates. And here's the urgency. JWST is still observing. More spectroscopic data are being collected. Deeper observations with JWST's NIR spec instrument will provide higher signal-to-noise spectra, allowing more precise measurements of line shapes and widths. X-ray follow-up with Chandra and XMM Newton will constrain the level of obscuration. Radio observations with ALMA and VLA will test whether any synchrotron emission can be detected. because if electron scattering is the correct explanation, future observations will confirm the exponential line profiles in all little red dots. If supermassive stars are the correct explanation, spectroscopic features unique to stellar atmospheres will be detected. And if dark matter seeds are responsible, correlations between little red dots and dark matter halo properties will emerge from large surveys. The truth is this: little red dots are one of JWST's most surprising discoveries. They appeared unexpectedly in the first images and have challenged our understanding of the early universe for 3 years. 3 teams have now proposed 3 different solutions. Within the next year, follow-up observations will determine which hypothesis is correct. And the only way to know is to keep observing, keep analyzing spectra, and keep testing models until the data force a conclusion. If this video left you uncertain which hypothesis is correct, hit like and subscribe to this channel. We are tracking JWST's observations of little red dots as new data arrive, and you will not want to miss what follow-up studies reveal in the coming months. Leave a comment with your prediction: electron-scattering cocoons, supermassive stars, or dark matter seeds. And share this video with anyone who thinks we understand black hole formation. After this, they will realize we are still debating the basics of how supermassive black holes are born.